Hello friends, this is Pratiksha Garud working as an assistant professor in MVP Samaj, Nasik. In earlier few videos, we have seen the MO energy level diagram for homonuclear diatomic molecules. Now in this video, we have to study the MO energy level diagram for heteronuclear diatomic molecules by taking an example of formation of HF molecule. So let's start with this. So we have to study the MO energy level diagram for heteronuclear diatomic molecules. So what are these heteronuclear diatomic molecules? We have seen homonuclear diatomic molecules means the diatomic molecules which are formed by the two same atoms. Based upon this, hetero means different. So the heteronuclear diatomic molecules, these are the molecules which are formed by the combination of atoms of two different elements, right? So their examples are, the examples of the heteronuclear diatomic molecules are NO, that is nitric oxide, CO, that is the carbon monoxide, HF, hydrogen fluoride, and the hydrochloric acid, that is the HCl. So these are the example of the heteronuclear diatomic molecules. Now in case of the heteronuclear diatomic molecules, as there are two different atoms, right? So as there are two different atoms, there will be charge separation, and hence we can say that the heteronuclear diatomic molecules, they are polar in nature. And when the heteronuclear diatomic molecules are polar in nature, we can say that there is a charge separation, and hence the bond formed between the two atoms is always a polar covalent bond. Okay, so this is the characteristic of the heteronuclear diatomic molecules. Further, we can say that we can use the LCAO principle for homonuclear as well as for the heteronuclear diatomic molecules. But the difference is that, or we can say that the application of LCAO principle for homonuclear and heteronuclear diatomic molecules is same. Only the difference is that in case of homonuclear diatomic molecules, we can write the LCAO principle as psi AB is equals to phi A plus minus phi B. But for the heteronuclear diatomic molecules, we can write the same principle as psi AB is equals to phi A plus minus lambda phi B. Okay. So where this lambda is the mixing coefficient. And in case of this, we can say that the lambda is not equals to 1 for the heteronuclear diatomic molecules. Or we can say that in case of the homonuclear diatomic molecules, the lambda is 1. That's why we are having this equation. Whereas in case of the heteronuclear diatomic molecules, this lambda is not generally equals to 1. That's why we are having the equation psi AB is equals to phi A plus minus lambda phi B. Okay. So we are having two different atoms, right? We are having two different atoms, so the energies of the atomic orbitals are also slightly different. So let's see the MO energy level diagram. So this is the MO energy level diagram for the heteronuclear diatomic molecules. Now we can see the atomic orbitals. So the sides we are having the atomic orbital. At one side, first atomic orbital, at another side, second atomic orbital, and at the center we are having the molecular orbital, right? And then the first atomic orbital is having the symbol phi A. The second atomic orbital is having the symbol phi B. Right? Then we are having the molecular orbital psi. Psi is the bonding molecular orbital, and psi asterisks is the anti-bonding molecular orbital. According to the LCAO principle, as we are having the two atomic orbital, there should be the formation of the two molecular orbital. Out of the two molecular orbital, the lower one is the bonding and the upper one is the anti-bonding. Now here we can say that the two different atoms, they are having the different energies for the atomic orbital, right? So we are having this psi A shifted to upper side and psi B shifted to the lower side, as their energies are different. This is the difference between the homonuclear and the heteronuclear diatomic molecules, right? So let us take an first example. First example of the heteronuclear diatomic molecule is the HF molecule. So what is this HF molecule? HF molecule is a heteronuclear diatomic molecule. So if you see this HF molecule, we can say that here it is formed by the two atoms. The first atom is the hydrogen atom with atomic number 1. That's why its electronic configuration is 1s1. Whereas the second atom is the fluorine atom with atomic number 9. That's why the electronic configuration is 1s2, 2s2, 2p5. Now this HF, in case of this HF molecule, the first atom, or we can say the hydrogen atom, is less electronegative than the fluorine atom. So we can write this hydrogen. Hydrogen atom is less electronegative atom, whereas the fluorine atom is the more electronegative atom, right? And when we form the atomic orbitals, right? When we form the atomic orbitals of the more electronegative atoms, contribute more to the formation of the bonding molecular orbital and less to the formation of the anti-bonding molecular orbital. Similarly, we can say that the atomic orbitals of the less electronegative atoms contribute more to the formation of the anti-bonding molecular orbital and less to the formation of the bonding molecular orbital. So what's happened due to this? So we can say that in case of the HF molecule, the electrons in the MOs, that is the molecular orbital, spend more time around one atom than the other. And hence, there will be charge separation such as the delta plus and the delta minus on the atoms, and due to which it develops a dipole. There will be a formation of the dipole on the molecule, and hence we can say that in case of the HF molecule, the covalent bond that is formed has highly ionic character. So this is regarding the HF molecule. Now in case of this HF molecule, we are known that it is formed by the two atoms. The first atom is the hydrogen atom with the atomic number 1. That means the electronic configuration is the 1s1. The second atom, the more electronegative atom, that is the fluorine atom, which is having the atomic number 9. That's why the electronic configuration is 1s2, 2s2, 2p5. Now, these 1s2 electrons or this 1s2 orbital, this 1s orbital is lower in energy, and as it is lower in energy, it is considered as a non-bonding. And hence, while writing the MO electron configuration, we have to use the letter K. Okay. Then, we have to form a bond between the hydrogen and the fluorine. From the hydrogen, we have to consider only the single electron, and also from the fluorine, we have to consider single electron, right? And that single electron is from the 2p orbital. That means these 2s2 electrons, they are neglected, and we have to consider only a one electron from the 2p orbital. So, we know that there are three 2p orbitals, which are there 2px, 2py and the 2pz. So out of these three 2p orbitals, only the 2px orbital of fluorine will be the most suitable one for the bonding. Why? This is because the 2px orbital matches in symmetry as well as in energy with the 1s orbital of hydrogen. So let's see this, how it happens. So we are having this. This is the 1s orbital of hydrogen. Okay, so this is the 1s orbital of hydrogen. Then we are having the p orbital, the plus lobe and the minus lobe, and this p orbital is of the fluorine, and which is the 2px orbital. So there will be overlapping of 1s atomic orbital of hydrogen and 2px atomic orbital of the fluorine, and due to their overlapping, we are getting the bond formation for the HF molecule, and due to this bond formation, there will be overlapping of the plus plus. That means the larger resultant will be the plus and the smaller will be minus, and this is for the HF molecule, right? And this is known as the sigma sp. Whereas if you see the other two 2p orbitals, that is the 2py and the 2pz, they are perpendicular to the bond axis. That means they are not of correct symmetry, and hence they remains as a non-bonding. Let's see this. So we are having the hydrogen with its 1s atomic orbital, and then we are having the remaining is the for the fluorine with the 2py or the 2pz. So we are having the 1s of hydrogen and 2py or the 2pz of the fluorine. Now here we can see that they are on of correct symmetry, right? So when they undergo overlapping, so due to overlapping we are getting this type of overlapping. So due to this overlapping, they are called as the non-bonding. So we are getting the formation of the non-bonding molecular orbital, right? So the overlapping of 1s orbital of hydrogen and a 2px orbital of fluorine, they gives rise to the sigma bonding MO and the sigma asterisk anti-bonding MO. So let's see the MO energy level diagram for the HF molecule. So we are having, this is the outline of the MO energy level diagram. We can say that at the sides, towards the sides, we are having the atomic orbital. At one side, atomic orbital of one atom, and at another side, atomic orbital of the second atom. Whereas at the center, we are having the molecular orbitals. As there are two atomic orbitals, there should be two molecular orbitals. Out of the two molecular orbital, one is the bonding, another is the anti-bonding. This is known as the LCAO principle. Now we know that in case of the HF molecule, the first atomic orbital for the hydrogen, which is named as 1s, and the second atomic orbital will be for the fluorine, and that is 2p, and here it is 2px, right? Now from the figure, we can say that the bonding MO and the anti-bonding MO, they are for the HF molecule, right? That means the molecular orbital, they are for the HF molecule, and they are having the symbol sigma sp, that is the bonding, and the sigma asterisk sp, that is the anti-bonding MO, right? Now from the figure we can say that the bonding MO, that means this sigma sp, it is nearer or it is closer to the 2p, which is 2px orbital of fluorine atom, and hence it has more character of the 2px orbital, right? Similarly, the antibonding MO is the sigma asterisk sp. This antibonding MO is closer to the 1s orbital of hydrogen atom, so it has a more character of the 1s orbital. So we can say that the 1s orbital of hydrogen and the 2px orbital of the fluorine, they differ in energy, right? And as they are differing energy, there will be lack of symmetry in the MO energy level diagram, and hence we can say that the HF molecule is the polar molecule, and hence the bond form will be the polar covalent bond. Now let us see the filling of electrons. Now we know that there is a single electron from the hydrogen and a single electron from the 2px atomic orbital of the fluorine. So we are having the single electron from the hydrogen, which is from the 1s atomic orbital, and a single electron from the 2px orbital of the fluorine. Now as there are only two electrons, both are first moved in the bonding molecular orbital, that is the sigma sp. So this is the first electron from the hydrogen and the another electron from the 2px atomic orbital of the fluorine. So this is the MO energy level diagram for the HF molecule. So based upon this, let's see the MO electronic configuration of the HF molecule. So we know that we are having the first atom is the hydrogen atom, right? And for that we are having the electronic configuration 1s1. Now for the 1s1 electron, we are having no electron that should be present in the K shell, because this single electron is used for the bonding purpose. Whereas the second, that is a more electronegative atom, is the fluorine with the electronic configuration 1s2, 2s2, 2px1, 2py2, 2pz2, right? Now here, this 1s2, that means these two electrons are 1s atomic orbital. It is lower in energy, that means it is a non-bonding, and for this we have to use the letter K. Whereas the 2s2 and the 2py2, 2pz2, these are neglected. Why they are neglected? Because we have to use only a single electron for the overlap with the 1s atomic orbital of the hydrogen. So based upon this, we are having the MO electronic configuration of the HF molecule, and that is K sigma sp2. So this is the MO electronic configuration of the HF molecule, right? So let's see the bond order. Bond order, which is given by the equation 1/2 into number of electrons in BMO minus number of electrons in ABMO. So which is equals to 1/2 into 2 minus 0. That means there are only 2 electrons in the bonding molecular orbital. So it becomes 1. So this shows that the bond order is 1, means there is a single bond between the hydrogen and the fluorine atom. Also, the HF molecule is a diamagnetic. Why diamagnetic? Because last entering electrons, they are paired in nature. As they are paired in nature, the HF molecule is diamagnetic. Okay. Then we can say that the bond length in HF molecule is 0.92 angstrom. And the bond energy is 135 kilojoule per mole. So, this is regarding the HF molecule. In the next video, we have to study the MO energy level diagram for the HCl molecule. Thank you.